Hello everybody, we're on the paper number 815 with the title Real-Time Autonomous Navigation with ResNet 18 and PyTorch based on AI computer jet Sonana. We're the professors, we're university professors, and some of the colleagues worked in both university, UNAG and Universidad Nacional Altiplano, both national universities in Peru. Well, we start with the outline and mentioning our objectives, checking on the system overview, also a small check on the communication network, our data set and methodology, the result of the research conclusions, future work, and acknowledgement. Our objective starts with the small context. We know that autonomous vehicles enhance safety and efficiency, but are expensive to research. Over the years, more and more autonomous cars are on the market and trying to integrate, but it's a long way. But a lot of research is need to be done, but some universities and don't have access yet fully to research. But there are hardware like Jetson Nano that uses GPU to train and test AI frameworks for machine learning experiments. So in this project, we will be using this small computers so we can test and see what the navigation is using AI frameworks. So starting with this, we will be design and build a low-cost autonomous vehicle prototype and implement ResNet 18 CNN and using Python for real-time control, validate navigation accuracy and performance on a modular test track, which will be on a small table where we can recreate a route. Our system overview is is like as we can see in the both pictures. In the right hand, we can see um, the all components put together above the mobile robot with two antennas. On the left side, we can see how it's connected the hardware for control, training, and test. And the Jetson Nano it can be integrated and also read and send commands and also be a computer. So that's the main element for this research, and also the camera for the visual input for training and then testing. So the robot will be controlled for an AI trained model. Communication network is as follows for this project. The robot will be communicating over wireless um, communication, so we can in a local network we can access to the robot and we can see what it's looking at, and also controlling with a gamepad control, and this will be used for getting and capturing image for training. So for training, we labeled as more than 2,800 images and collected across different scenarios, which are different lines and um, angular forms of the road. So we train all this in after collecting all, but trained separately. So we've trying to find the most and the accurate model or the best samples for training. So we will validate and find the optimal. So after training, we saw that at the optimal a epoch we achieve some balance and accuracy. So, but we had to go across the five scenarios to find out that. So, as we see, we had our data set, and this data set basically collects and we try to label an XY point in the image, which are the middle line that goes between the line and the road, so we can say so the AI can get and try to learn or not overlearn the central point of the road. So all these are saved and count. As a result, we see that after many tests, so we found some optimal performance on the robot. So at the highest point and with the small data at the beginning with 10 to 20, less than 10 epoch, we can see that the robot can easily achieve some distance in our road. So but the highest and the longest distance made by the autonomous robot, it's the 208 six 288 centimeters, which are the most longest road that the robot followed. So that will be our best setup for this robot. And also we see that overfitting is observed at 8 on epoch, at 70 epoch, and we can say that the Jetson Nano is a small computer, but it handles very well some experiments based on training and test. So when compared with the another works, so previous JetBot implementation have some lowest and very um, some varies close to the 70% of success rates. Our system achieved almost 70 with improved some with improved data and tuning parameters. So we validate the reproducibility using the Jetson Nano hardware. So below we see how the robot is following a track, and the image next to it is that we train this yellow line as a center point, so the robot always can follow this line. Well, this is our conclusions. As we can see, as we will be seeing the video below, the Jetson Nano efficiently executes the real-time machine learning control. And now currently the robot is already trained, so that has some drifting and offset sometimes due to the mechanical structures. Well, then ResNet 18 provides balance between accuracy and efficiency. Demonstrate and well, the third demonstrates scalable low-cost approach for AI education. So this kind of research shows us that autonomous navigation can be achieved with small and very affordable components like Jetson Nano, because that can help us to understand much better how these AI autonomous driving systems can be achieved and how we can start testing from our institutions for educational purpose. We try to expand our data set in the future with better and variation the lighting environment, evaluate mobile net and efficient net, which are some other architectures. Um, then also integrate 3D printed chassis and high resolution cameras. Explore options like Jetson or RIM uh, for improved interference in like speeding up like the AI frameworks. And we acknowledge our universities, both based in Puno, Peru, Universidad Nacional Altiplano, and Universidad Nacional de Juliaca, which we partner and we are very close universities with great relations in research. And also, we appreciate the Chilecom 2025 event and the organizers. We are very thankful.